Swayam Prabha. Digital India. Educated India.
Good afternoon. Welcome to the course on comprehensive view of speech processing. Today's lecture is 29 in this series, and today we are going to discuss about the statistical pattern recognition, a new topic which we started yesterday, and today we are continuing that. So, this is the overview of the various topics that we are going to cover under the statistical pattern recognition. It is a very broad area, and since it is required for developing speech systems in the context of pattern recognition. So, therefore, here we are very briefly discuss about terminology, and these things will be in turn used later on for the specific techniques that are used for the speech models to perform various speech tasks. And here in this yesterday we discussed about what is meant by the pattern classification. So, this we discussed with a very simple example of handwritten character recognition. So, in that handwritten character recognition, we considered, to make the problem to be simple, we considered the recognition of two characters A and B, which are the characters are written by from the cursive script, taken from cursive script written by humans. So, as a simple two class problem has been considered, and in that context we discussed about basically what is meant by the pattern classification and all. And then from that example itself we derived that what is the need for pre-processing and what is meant by feature extraction. So, these concepts also we have discussed. Basically, like from the pattern classification point of view, directly if you use the raw features or the raw pixel values. So, we come to know that there is a huge number of images that are required to have like kind of a template matching. So, to overcome that we need to have some pre-processing is required, and sometimes even that pre-processing techniques are also can be considered as a feature extraction. And for performing that we should have some little domain specific knowledge is required. And then we also introduced the term known to be curse of dimensionality, and we have seen that when you are extracting the features, as we increase the number of features, the discrimination between the classes can be increased. So, with that the classification accuracy will be improved, and in turn the error in misclassification will be reduced. So, therefore, but there is a limit for that as you keep on increasing the number of features, and that introduces a problem known to be curse of dimensionality. And we have seen that how this curse of dimensionality will be come into the picture as the number of features are increasing. Then afterwards we discussed about classification and regression, and here these two terms, the classification we already mentioned, and regression is also very similar to the classification, and these two can be viewed under the framework of function approximation. So, when you are approximating a function or when you are trying to model the underlying function of a system, so the system that depending upon the outcome of a system, so we can view that as either a classification problem or a regression problem. Usually in case of classification problem, so it will be the output will be a discrete, a number of classes, as we have given some examples of related to that, like a speech recognition problem where the outcome will be like one among the 40 phonemes or 40 sound units. And similarly in case of handwritten character recognition, so where here also the number of classes will be 26, and whereas the regression problem is nothing but the outcome will be a continuous quantity. And the examples what we quoted there was like a stock price prediction. Like it means that by having a history of the stock price for past few weeks or past few months, and from that knowledge we will try to predict the stock price of today at this moment, right. And similarly the weather forecast and also by having the knowledge about the weather in the preceding days, So, we will try to predict the weather of today or tomorrow and so on. So, in that case also both in the examples quoted, weather forecast and or weather prediction or this stock price prediction. So, both the outcome will be a continuous quantity, and similar to that in the context of speech also we mentioned another example known to be duration prediction. So, this is required when you are when you are trying to synthesize the speech by machine, where we need to know about like what will be the duration of each of the sound units that need to be synthesized. So, in that context again the duration of a sound unit is again a continuous quantity. So, all these are the examples to a regression problem. Then we also started the topic of estimating the mapping function. So, as we have seen that there will be a system can be considered as some underlying function used to be there, and from that suppose if you can able to, if you are modeling a system means, so we try to model or we will try to capture the underlying the functionality of a system, right. So, it means that if you can capture the underlying functionality of a system, then by giving inputs the outputs will be the similar to the way the system output, very similar to that. So, in that case how do we capture the system, how do we estimate the underlying function that is present in the system and all. So, for that we have considered an example like the polynomial function or polynomial curve fitting. So, with that the system function can be like you can able to approximate or can able to determine by using the polynomial coefficients or the coefficients of the polynomial. So, that we discussed in we started the yesterday, and today we will continue that. So, here as we have seen that the underlying function, to model underlying function using a polynomial curve fitting. So, we can say that suppose y is the output of a function and x is the input. So, therefore, the output depends on a function of input as well as these coefficients, the polynomial coefficients and all, these polynomial coefficients, like this w is nothing but these polynomial coefficients. So, therefore, y that is output the system output is a function of input and this w like the weighting coefficients, and here the modeling a system is nothing but we need to estimate that how many these weight coefficients are required and what are those values. How many weight coefficients are required, that means it is nothing but the degree of the polynomial that is required to model the underlying function, and then once you know the degree of the polynomial we come to know that how many coefficients are required, then afterwards what are those values, what are the optimal values of those the weight coefficients. So, therefore, here y equals to f of x comma x w, x is the input and w is the weight matrix, or you can say that the weight coefficients in the case of the polynomial. And now here for modeling this particular system are nothing but modeling these polynomial coefficients. So, here we consider that input will be like x1, x2, xn, these are the inputs. That means, for these x1, x2, xn inputs, the corresponding outputs from the system will be like t1, t2, tn. So, these are the x1, x2, xn are the inputs and the t1, t2, tn are the like the corresponding outputs of the system and all. So, here by taking these examples, that means the corresponding x1 to t1, that means when you give x1 as the input and t1 will be outcome, when you give x2 as the input and t2 will be the output, when you give xn as the input, tn will be the output. So, by giving these the pairs of input and output, then we need to predict the system, the underlying system function and all. So, here the underlying system function is prediction is nothing but like estimating the degree of polynomial degree and then the coefficients of a polynomial and all. So, here assuming that the underlying function that need to be estimated will be the sinusoidal function. So, therefore, there is a sinusoidal function sin of 2 pi x and then some multiplication constant and then some additive constant. So, so the underlying function h of x is this one 0.5 plus 0.4 times the sin of 2 pi x. So, it is basically it is a sinusoidal function, right, and now we need to estimate that. So, for that to provide a variability, otherwise it is a deterministic function, right. So, therefore, to give a variability, what we need to do for the h of x, we are adding some random noise of known distribution like some Gaussian distribution with some mean 0, right, and with that means we are giving xn as the input and then we are computing the outcome as h of x plus random noise, whatever the random noise giving at that particular instant of time and all. So, that way here the random noise samples also are taken from some distribution. So, therefore, x of n as given as input, and your the outcome will be nothing but h of x plus the random noise the value at that particular input, right. So, that way you can able to find out the your like y output, and now we need to see that the as we know that when you give x of n as the input, the output will be t of n. But here when you give x of n as the input, you can see that some other when you apply to a function, you will get outcome as y of x n comma w. That means we are modeling this with respect to the polynomial function. So, therefore, to better estimate the polynomial function here, so we need to, as I mentioned, that we need to know about we need to like estimate the degree of a polynomial and its coefficients, right. So, therefore, here the error in our prediction will be like, suppose for example, if we choose the degree of a polynomial equals to 1, then it becomes the y of x equals to w naught plus w 1 of x. It is nothing but it's a linear function. And suppose if you assume that the degree of a polynomial equals to 2, then it becomes a quadratic function. So, it is nothing but w naught plus w 1 plus w 2 x square. Otherwise, if it is a cubic function, then one more coefficient will be considered, that means order of a polynomial will be 3. And if you suppose if you assume that the complexity of a system is very high, then we can go for the higher orders of polynomial, maybe m equals to 10 or so, likewise 10 or 11, something like that, right. So, that way when the depending upon the choosing a polynomial order, so here we can able to estimate its corresponding output, and then we can able to find out the error. But we know that for a given x of x input, that means x 1, x 2, x 3 and so on, we know that the target output will be t 1, t 2 and so on. And since we do not know the underlying system, we need to estimate the function. So, therefore, here we are choosing a polynomial, and based on the polynomial function we are computing output, and but we know the actual output. So, therefore, the difference between the computed output from the given polynomial, from the assumed polynomial, and then the actual output, the difference becomes the error. We are taking the square root of the error, the root mean squared error. It means that we are computing the squared error across all the examples, and we are summing up, and then we are taking square root of it. That becomes RMS, that means root mean squared error and all. It means that we are taking a square of error, and then we are summing up all those error components with respect to all the examples, and then we are taking a square root of it. So, it becomes ERMS. So, that way this is this term is the like root mean squared error and all, right. And so, yeah, these things we have already discussed, like examples to the function approximation, like whether it may be like classification problem or regression problem. Yeah, here these things also we introduced, we discussed in the last class. So, as we have seen, suppose we choose, if we assume that suppose a priori we do not know the characteristics of a function. So, therefore, we will try to model the function, try to model the system with a simple function or with a first order polynomial. Then in that case, like m equals to 1, then in that case the order of the polynomial will be 1, it is a linear function. So, therefore, we know that these are here the circles indicates the outputs, the actual outputs of a system. So, therefore, based on this we will try to the function whatever we have chosen, the polynomial of order 1, that gives you the best fit function is nothing but this one, because if you look at this one, it is a line, because when you take only consider m equals to 1, then the function becomes w naught plus w 1 of x. It is nothing but it is a linear function, it is nothing but it is a equation of a straight line, and here for the given data points, the straight line, the best straight line that fits the data will be this one, because this is the orientation of the straight line. So, with that you can see that there are some points which are on the top side, upper side of the straight line. There are some points that are at the bottom side of a straight line. So, that way the straight line will be just passing in the middle across the points. So, this is the best possible function if you consider the polynomial of lower order and all. And suppose for example, if you consider the polynomial of cubic function, like if you assume that cubic polynomial is considered, that is if m equals to 3. Then with that, if you try to model the data from the given data, if you try to model the function, you can able to see that the here the solid thing is indicating the approximation of the polynomial for the given system and all. And if you look at here this polynomial, the solid line here, this is very close to the approximation of a sinusoidal signal, where our underlying system itself itself resembles the sinusoidal function. So therefore here if you take a cubic polynomial, it means a polynomial of order 3, then it tries to it tries to model the system in a very better way. It is very close to the actual representation of a system and all, because the actual representation of a system is the dotted one, you can see here. And whereas the model by using a cubic polynomial, the polynomial model the system using a solid line, using the solid one. So they are like both are very close, and the general trend has been captured, that is important, right. It is not that every day the predicted or the model function may not give 0 error for all the points, but you can see that the model function, the trend of the model function or the shape of the model function is almost very close to the actual function, the underlying function of a system and all. So that way you can say that here in this context you can say that the cubic polynomial can able to estimate the function in a very effective way in this context. Suppose without knowing this, suppose if you increase the degree of a polynomial, for example, if you make m equals to 10 for example, it means a 10th order polynomial. That means there are a lot of nonlinear terms are there present in the polynomial, so that the very complex system can able to be modeled. But here the system, the underlying system is not that complex, it is just a sinusoidal function, it is a smooth sinusoidal function where is an alternative way like a positive and negative and all, right. But here if you try to for that model, if you choose the 10th order polynomial, you can able to see that the polynomial, the 10th order polynomial tries to model the underlying behavior of a system like a very noisy way, because it has a lot of oscillations. You can see it tries to see that for every data point the function should pass through that. Every data point should be lying on the function. So for doing that, what is happening is that for every data point you can see that here for this, if you try to estimate, you will see that the function goes to a higher value. Then afterwards when you see that there is a point which is very below, so therefore immediately the function tries to suddenly come down, and again afterward there is a next point which is at a higher level. So therefore here what happens is that if you choose the higher order polynomial, because of high nonlinearity that is embedded in the polynomial, so with that it tries to model the behavior or model a function in a very nonlinear way. It gives you a lot of oscillations will be present. And if you look at here at a gross level, if you look at the model that is offered by the 10th order polynomial, it is not at all resembles to the underlying the function. The underlying function is a smooth sinusoidal function, but here the function that is offered by the 10th order polynomial is highly oscillatory and noisy and all. But if you look at the error with respect to the training data, the error will be 0, because here all these oscillations somewhere the point will be lies on these oscillations or these the function that is offered by the given model. It means that the function tries to fit the given data, training data, but it is not capturing the generalization behavior or the overall behavior of a system and all. So that is the reason that for all the training points, given the 10 or 11 training points, the function is passing through that. So therefore it offers a 0 error for the whole training data. But if you look at the overall behavior of a system, it is not at all captured at all. Instead it is a very highly oscillatory and noisy and all. So therefore if you try to look at from a generalization point of view, or so far we have what we have seen, the underlying function is a sinusoidal function. With that, when you try to model by using a polynomial fit, where a priori we do not know the functional behavior, the underlying system. So therefore if you try to capture with very simple model like with very fewer number of coefficients, then it becomes a linear function. So, with the linear function as we have seen that it offers a simple straight line, but the actual underlying function is having some nonlinearity, which is nothing but a sinusoidal function. So, therefore, the model the predicted model or the predicted function which underfits the data and all, which not at all properly fits the data at all. So, therefore, it leads to some error and all. So, with that, if you increase the complexity and when you reach to the cubic polynomial, then you can able to see that the function whatever is estimated is very much close to the underlying function and all, right. And still if you increase further, you can able to see that the error has been come down or error will be reached to 0 for the higher order polynomial, like for 10th order polynomial, but the function whatever is captured is not at all resembles to the actual the behavior of a system or actual the underlying function of a system and all. So, therefore, here if you look at here this diagram, particular diagram, where here the RMS error has been plotted with respect to the order of the polynomial, and here if you look at here, this solid line is the error that is offered with respect for the given training data. So, therefore, if you look at here the error will be reduces as you increase the order of the polynomial, right. So, if you see that from like without from the single and linear function, then afterwards quadratic function, then the cubic function, the error has been come down. From the cubic function further, if you increase the order of a polynomial, you can see the error will be slowly decreases, and then when you reach to the 10th order polynomial, the error will be 0. So, it means that for a 10th order polynomial, all the training data points they lie on the function that is estimated and all. So, therefore, the training error will be 0, right. But here if you see that in the same plot we have a dotted line. So, this dotted line indicates the error with respect to the test data. Test data means actually here the training data means by using this training data we will try to model the system, or you can say try to predict the underlying function, and after that we have to test the system or test the function, the estimated function, how far it is accurately predicting for unseen data. So, therefore, when you give the unseen data or when you test the system with unseen data with the different polynomial functions of different orders, you can able to see as the polynomial order increases, right, up to some extent for the test data you can see that for the test data the error will come down, and afterwards if you further increase the order of a polynomial, you can see there is no decrease in the error at all. Instead, sometimes you can see that there is increase in the trend of error also, because the reason is that for a training data you can see that the error has been come down to 0, but whereas for test data, even for the 10th order polynomial, because since the 10th order polynomial is not properly captured the underlying behavior, it just tries to fit the given data. Therefore, for training data the error is 0, but for test data you can able to see that the error is not at all 0, the error is maybe increasing, right. So, you can see the minimum error is observed at 3. It means that this is the best model, or you can say the optimal model, the polynomial which represents the true system function, true underlying system function and all, because till that it has been decreased, and afterwards there is no decrease at all, afterwards there is no decrease in the error for unseen data. It means that this point, the minimal point here, whatever is there for test data, it indicates the optimal complexity of the system. It means that for a given system, the order 3 polynomial or a cubic polynomial is reasonably good for capturing the underlying function of a system, or you can say that it best generalizes the system behavior with a cubic polynomial, right. So, therefore, here with that actually here we are trying to introduce another term related to the pattern recognition known to be generalization. It means that actually when you are trying to model a function or when you are trying to estimate a function, underlying function, the function that need to be estimated should be generalized, it means that it should generalize or it should capture the overall behavior of a system. It is not that the function whatever you are estimating, it is not just fit the training data, it is not good enough. It tries to capture the underlying characteristics or underlying relations that exist in the system has to be properly captured by the given system and all. So, that is known to be the generalization, the concept of generalization and all. So, here we have analyzed the previous function, sinusoidal function, underlying sinusoidal function estimated by different degrees of polynomial. So, from that what the observation here is that as the degrees of freedom here the degrees of freedom is nothing but the number of free variables, it is nothing but number of weight coefficients in the context of polynomial curve fitting, right. So, as the degrees of freedom increasing means actually here it is nothing but number of weight coefficients we are increasing. So, with that the order of the polynomial is increasing, with that it tries to capture or it tries to become more and more complex and tries to capture the more complex relations that are present in a system and all, right. If the system is really complex, very heavy, highly complex, at that time you need to go for the higher order polynomials, like you need to go for beyond a cubic polynomial where it tries to model the behavior very effectively and all. If the underlying function of the system is not that complex, then in that case there is no need to go for very higher order polynomials. It unnecessarily provides the oscillations in the mapping function, it becomes very noisy and all. So, in that case when you test the data with unknown data, then you can that leads to lot of errors and all. So, therefore, here the degrees of freedom is nothing but the number of weight coefficients or the degree of polynomial. So, as you observed that the lower degrees of freedom, that means the lower degrees of freedom gives you the higher bias. It means that it is not to be underfitting. That means for a given data, as we have seen earlier, the lower you can see here. So, this is the lower degree freedom, that means here we consider the polynomial of order m equals to 1, it is nothing but only two coefficients are here, w naught and w 1, it is a linear function. So, with that what you can see here, the error is more and at the same time here the bias is more, like here whatever the w naught w 1. So, with that the function will be biased. So, therefore, it underfits the data. You can see that there are a lot of data points which are not at all close to the given function and all, right. So, therefore, it underfits the data and the other ones are like you can see here, this one whereas the other extreme, whereas the higher order the more degrees of freedom, where you can see the error will be 0, but it overfits the data. You can see that for a given data points the function is passing through the data points, and except that the overall shape of the function, if you look at that, it has become very oscillatory and lot of transitions are there, right, lot of oscillations are present, it appears to be very noisy and all, right. But this is not the actual trend or actual the function, underlying function. The actual underlying function is the smooth sinusoidal, but here whatever we estimated is like more of transition. You can see at the beginning we have a sudden rise is there and again sudden fall and again rise fall and all. So, it becomes lot of oscillations and it is a very noisy thing, right. So, whereas the in between some intermediate polynomial order like a cubic polynomial, where you can see that the estimated function is very close to the actual function, right. So, that is what here you can see here, the lower degrees of freedom provides the higher bias. It means that it underfits the data, that means lot of data points are away from the actual function that was captured. It means that it gives you a lot of error, whereas higher degrees of freedom gives you the higher variance. That means there is a lot of variability in the function, the captured function. That is what we have seen. There are a lot of oscillations were there, lot of transitions were there. It is known to be variance. So, therefore, here with the higher degrees of freedom we have a higher variance will be offered. So, with that the data will be overfitting, that means the estimated function overfits the data. It means that all data points, tiny data points may lie on the given function, but when you try with the new unseen data, the unseen data may not be give the proper outcome, may not be predicted properly, right. So, it is a overfitting and it is noisy, right. So, generalization is nothing but trade off between the bias and noise, that means the bias should not be too high and even the variance should not be too high. So, the good generalization gives you lower bias and low variance and all. It means that when you are trying to model a system, we need to see that the model complexity, effective complexity has to be captured by using the lower bias and low variance end. So, if you see the example here, as I mentioned here, you can see the best generalization is nothing but, as we have seen what already we come across, the complexity of model should be complexity of model is neither too small nor too large. If you assume that, or if you try to model the complexity with very less complex or very less complex model, it is nothing but a linear model, then we end up with a bias, higher bias, right. And whereas the other way, if you try to model with the high complex model like a higher order polynomial, where we end up with a lot of oscillations, right. And so therefore, the model, when you are trying to capture the underlying function, the complexity of model should not be neither too small nor too high, right, because we have a problem. If the model is very less complex, we end up with the bias, and if the model complexity is too high, then we end up with a variance, lot of variance, high variance and all. So both of them, the higher bias or higher variance and all, it is not the desirable thing. So therefore, optimal complexity is required, right. So here, if you look at here the data, suppose these are the data points, right, and by using these data points, suppose if you use the linear, by using a linear polynomial, if you want to separate, you can see this is the plane, with that you can able to separate it out, with the plane you can able to separate it out. That means, when m equals to 1, when you choose the model complexity of polynomial m equals to 1 or 2, you can able to see that with 1 you can able to see it is a linear plane, where you can able to separate the two classes to some extent, right, in this case, in this example, right, because here the underlying function will be just, you can see the data points of the two classes like crosses and circles, where even the linear function is good enough, even the linear function is good enough to capture the underlying behavior of a system between these two classes, right. So with a linear function, linear line, straight line, you can able to separate it out, or otherwise if you slightly increase the complexity, like instead of linear, if you use the quadratic or a cubic polynomial, you can see that the separation surface, right, you can see that it is a curved surface, where the data points will be separated and all. So even this is also okay to some extent. For the given example, the data points, you can see that you can able to separate these two classes using either a linear plane or even a quadratic or a cubic polynomial, right. But if for this same example, if you try to model with a very higher order polynomial, it means using m equals to 11, right, that means using the 11 coefficients or nothing but 10th order polynomial. If you do with that, then what happens, the error surface or the separating surface, the model, the function captures will be something like, it is highly nonlinear. You can see lot of transitions are there. What it will do is that it tries to exactly fit to the training data, because the training data, wherever the class points are there, a specific class point, it tries to preserve that from the other class. So therefore, the surface or the separating boundary, you can see that this is a nonlinear boundary, and this will be captured by using the higher order polynomial, right. But the actual behavior, general behavior will be like this. You can see that with the line, the upper portion of the line will be one class and the bottom portion will be another class, or otherwise if you take a parabolic curve or some polynomial, the cubic polynomial, where the below the curve will be one class and above the curve will be another class. But here you can see there is a lot of transitions. Here for this you can see, by using this curved surface, for the given training data it can separate, that means there is no like misclassification at all. But if you choose these things, you can see there is some misclassification, very few points there are misclassified. Here you can see there are circles this side also, and there are like a plus sign or cross signs this side also. Similarly here also there are the classes, the circles are this side, some circles, and a few crosses are this side also, right. But here you can see, by using this highly nonlinear surface, you can see there is no misclassification at all. But this is not desirable, because this is not the true behavior of the classes, right, or the discriminating surface between the classes and all, right. So that is what here we have mentioned here. So the optimal generalization is nothing but controlling the effective complexity. That means for a given system, we need to measure or we need to estimate the effective complexity. If the system is really complex, then you have to go for higher order polynomial. If the system is not that complex, then you have to go for a simple model like a linear polynomial, like that way. So that way you can see, if you use a polynomial fit with m equals to 1 or 2, you can able to see that the surfaces will be very clearly discriminate the two classes and all, like m equals to 1 or 2, where it is a simple model, it would fit. Not this one, actually you can see this, and whereas the m equals to 4, where you have cubic polynomial, where it is optimal model that best generalizes the generalization of the system and all. And whereas if you choose m equals to 11, that is a 10th order polynomial by including w naught coefficient, right. So, you have a 10th order polynomial, it is very complex model, it tries to overfits the data, but this is not desirable, as I mentioned that. We should have the model, whatever we build the model from the data, the model is a generalizable one. It means that the underlying characteristics of a system has to be captured. So, that is the requirement when you are modeling a system and all. So, therefore, here we should avoid this one, we should avoid the overfitting of a data because here a priori given the data points, we do not know whether the data points are arrived from a system having very complex system or less complex system or a moderate complex system, that we do not know. We have only data points are available, right. So, from the data points we need to estimate the underlying function. So, for that what we can do is that, so we will try to, like for example, to find out the effective complexity, what we can do is that for the error term we will add some like the regularization term. It means that suppose if you try to model with a higher order polynomial, right, and if you try to capture the data, capture the function, and the captured function becomes highly nonlinear, at that time these oscillations will be overcome. That means, wherever the oscillations are present in the captured function, at those oscillations it gives you the higher value, and that adds to the error function. So, that the function whatever is captured will become a smoother one. So, here what I mean to say is that, for example, here on this you can see the transitions at different places and all. So, therefore, to overcome these transitions, here the error will model the effective complexity by adding a penalty term to the error function. So, here you can see E cap is the error that we are using here to overcome the overfitting of a data, where E is the actual error, and here the gamma, this one, the regularization term, here you can see that the omega, gamma omega, r omega, gamma omega, where you can see this omega is known to be regularization term and this gamma is some constant, and this regularization term that depends upon, here it acts like a smoothing factor, right. So, it means the regularization term is nothing but say d square y by dx square we are calculating and square of that. So, d square by dx square, wherever there is oscillations are there, and if you compute the d square y by dx square over that, it gives you a value, larger value and all. It gives you a larger, that means wherever the noisy surface is there or wherever the sudden transitions are there. So, there the d square y by dx square will give you the offer the value. Otherwise, if the curve is very smooth, then the d square by dx square will offer the 0, because if you have a straight line, if you perform twice differentiation, you will get a 0, or if you get a smooth surface, on that if you perform the second order differentiation, that gives you the 0. So, therefore, what I mean to say here is that here we design the error function such a way that the error for a, in case of smooth surface, here this particular term, the added term will give you, will offer the 0. Right. Whereas, if the error function, if the mapping function that is captured will be highly nonlinear, very oscillations, then it adds value, then it gives you some value, positive value, that adds to the error. So, it means that the error will be increased in case of this, the oscillatory behavior of a mapping function and all. So, wherever the oscillations were there, at those places when you take a second order differentiation, that gives you some value, right, variance. Right. So, therefore, that way you can by varying the error at a higher oscillated mapping function. So, with that we can able to control the complexity of a system and all. So, that way by using a regularization term you can able to control the complexity. So, with that we can able to achieve the generalization where the polynomial order can be controlled, should be neither high or not too low. So, that way you can able to get a right order of a system and all. Yeah, next, after discussing about the function approximation, now we come to the last point, that is Bayes theorem, and here the Bayes theorem is a framework, probabilistic framework, with which we can able to to perform a classification in a way, automatic way. How do we do it? how can we perform it, right. So, for that we can use a Bayes theorem. The result of a Bayes theorem can be used, with which we can able to given the data or given the feature vector, and we can able to like estimate that whether this feature vector belongs to which of the classes, right, and we will decide the which class the corresponding feature vector belongs to, right. And here for this, here also we will take an example of the two class problem what we have considered at the very beginning in the discussion. So, just if you try to recollect that, we considered the two class problem where the two classes are, one is the class 1 corresponds to the alphabet A, which is a cursive script or written by human written symbol, like a handwritten character, and similarly the class 2 corresponds to the handwritten character corresponds to B, right. And so, we know that based on the shape of the characters, if you take the height by width ratio for class 1, that is for alphabet A, the height by width ratio will be smaller, and whereas for alphabet B, the height by width ratio will be higher, right. So, here to design the problem, classification problem using the Bayes theorem. So, what we are doing here is that, so here just you consider here, take this diagram here. Here we have like two classes, class 1 and class 2, right, and the class 1 corresponds to like the examples of A, alphabet A, handwritten A, and class 2 corresponds to the examples of B, handwritten character B and all. And here this XL is nothing but the height by width ratio that we have seen. The XL is nothing but it is a feature derived from the image, where the image contains the alphabet either A or B, and for that from the A and B we will try to derive the feature like x1, which is nothing but height by width ratio. It is nothing but number of pixels, height is nothing but so many pixels and width is another number of pixels. So, by taking a ratio, that ratio gives you the x1 feature and all. And now for example, here in this case we consider that we are consider total there are 100 examples we have considered, and in that assuming that out of that the 70 examples are belongs to class 1 and the 30 examples are belongs to class 2, right. So, we have taken some 100 examples, out of that the 70 are class 1 and 30 are class 2. It is nothing but 70 belongs to 70 corresponds to character A and 30 corresponds to the character B, right. So, from each example or from each image we captured we try to determine the height by width ratio. So, that way from each image we will get one value, the height, the feature like x1 we can able to compute. It is a scalar value, it is a value, one value we will get, right. So, likewise for each example, for 100 examples we will get 100 values, and those 100 values they are ranging from like some lower value to some higher value, and we divide that range into some number of bins. You can see here these are the bins, like here in this case just for representation purpose we made it like 8 bins, right. So, in these 8 bins here these are the points, like here in the first bin there are there are 2 examples corresponds to class 1 were there, and in the second bin there are 5 examples corresponds to class 1, and see here in this example like you can see x1 is nothing but height by width ratio, and as I mentioned that the alphabet A contains the lower height by width ratio and alphabet B contains the higher height by width ratio. So, that way if you look at the number of examples also, at the lower side you have the class 1 examples are more, and at higher side you have a class 2 examples are more. At lower side there is no class 2 examples at all, right, and similarly at higher side there is very few or almost like in some bins there is no class 1 examples at all. So, this is intuitive, right, and now here I have taken 100 examples, those 100 examples I computed the features, and those features as per the bin, as per their range I just placed into corresponding bins. There are total 8 bins were there, out of 8 bins all these 100 points were placed based on their value and all, right, and again according to the class 1 and class 2, right, and here yeah, class 1 and class 2, and x is the data vector, and here suppose here I am just introducing some probabilistic framework to compute the to determine the like a classification or to decide to design a classification problem. We are using a Bayes theorem, and here I am just introducing some terms, some basic probabilities definitions which we come across already, and here here you see the probability of Ck comma x, this is the joint probability. Probability of Ck comma x is known to be joint probability of x and Ck, right, and this can be written as probability of Ck comma x, the joint probability of Ck comma x can be written as, using the conditional probabilities you can able to write like this, probability of Ck comma x, joint probability of Ck, that k may be either 1 or 2, x is a vector, x is the feature vector. So, the joint probability of class 1 comma vector or a class 2 comma x, class 2 comma vector. So, that you can able to write it as probability of Ck given x into probability of x, or probability of x given Ck into probability of Ck. Here this probability of Ck given x is known to be conditional probability. It means that what is the probability of class Ck by given a particular feature vector, and similarly what is the probability of a feature vector given the class, that means by knowing the class what is the probability of this particular vector. So, these are known to be conditional, that means we are here we are computing, we are assessing the probability of either a class or a vector like conditioned to the other quantity, right. So, therefore, these are known to be conditional probabilities, probability of Ck given x and probability of x given Ck, conditional probability, and this joint probability can be estimated by using these two expressions, either of these two, like both are same, either probability of Ck given x into probability of x or probability of x given Ck into probability of Ck, right. Okay. And now we know that from the examples, you know that there are total 100 examples, out of that the 70 belongs to the class 1 and 30 belongs to class 2. So, with that we know that the probability of C1 is unconditional probability, that means probability of C1, right. We know that there are 70 examples are there out of 100. So, therefore, probability of C1 is nothing but 70 by 100. Similarly, probability of C2 is nothing but 30 by 100. So, these are known to be prior probabilities, that means the probabilities are known from the data itself. So, by knowing, if suppose we have a data in our hand, data is known. So, from the data we will try to see that how many examples belongs to class 1, how many examples belongs to class 2, right. So, likewise for each class we will try to find out how many examples, then afterwards the fraction of a specific class examples by the total examples gives you the prior probability. So, that way here the 70 by 100 or the 30 by 100. So, these two are the prior probabilities of class 1 and class 2 respectively, right. And now here you can see probability of Ck XL, that is joint probability of Ck comma XL can be estimated likewise. Suppose for example, if you want to compute probability of C1 XL, here XL belongs to this particular bin, right, and probability of C1 comma XL, that is the joint probability of C1 XL. What is the joint probability of C1 XL, C1 and XL together. So, we know that this is the C1, right, and here this is the XL bin. Out of this, if you look at here in this, that means the overlapped bin or overlapped area here belongs to C1 as well as XL will be, it contains, there are 7 points are there, probability of C1 comma XL, there are 7 points, that means there are 7 examples falls in this particular cell, right. And what we want here, the C1 comma XL, that means joint probability of C1 and XL together. How many? There are total 100 examples are there. Out of that, the joint probability of C1 comma XL is nothing but here from this diagram you can say that it is a 7 by 100. Likewise, probability of C2 comma XL, like probability of C2 comma XL, there are 3 examples were there in this particular cell out of the total 100 examples. So, you can say the 3 by 100 and all, right. So, the same thing you can also write in terms of these definitions. You can say this is the joint probability of C1 comma XL or C2 comma XL, that can be written as probability of XL given C1 into probability of C1. What is the probability of XL given C1? Probability of XL means this one, this is the XL cell given C1, this is the XL given C1. So, this is XL and given C1 means actually there are, we know that there are 70 examples are there in the C1. Out of the 70 examples in the XL cell, right, the number of examples that are here will be 7. So, therefore, 7 by 70 is given XL given C1. So, that means XL given under C1, how many examples are there in XL? That is nothing but probability of XL given C1, that is 70 by 7 by 70, right, 7 by 70, right, and then probability of C1. What is probability of C1? Probability of C1 70 by 100, right, because we know that there are 70 examples out of all 100. So, So, therefore, 70 by 100. So, that gives you 7 by 100. That means, here as I mentioned, the joint probability of Ck comma x can be written as using the conditional probabilities and prior probabilities, right. So, this way you can write. So, you can by definition also you can get 7 by 100, and by using a joint probability also you can see that. So, that way the definitions whatever here we mentioned, they can able to tally, or they can able to we can also see that with the numerical examples also, right. Probability of C1 is 7 by 100, right, and similarly probability of C2 comma XL can be, there are 3 by 100, right. C2 comma XL is not the 3 by 100. So, that can be written as like this way, even XL given C2 into probability of C2. So, that way you can also get. So, from this what we can see here is that the you can write the joint probability as in terms of conditional probability and prior probabilities, and we have considered the classification problem contains 2 classes where there are 100 examples. Out of that 70 belongs to class 1, 30 belongs to class 2, and then we have just verified this the basic probability results using this numerical example and all. Yeah. Next we move on to, like here the actual Bayes theorem here can be here this is the joint probability of Ck comma XL can be written in terms of conditional and prior probabilities, right. You can see here probability of Ck given XL into probability of XL, or probability of XL given Ck into probability of Ck, right. Either way you can write. And now here from this result, right, you can say that this is a joint probability, and that is nothing but equivalent to these two, right, in terms of conditional probability and prior probabilities. And now here in this, here if you look at here the probability of Ck given XL, it means that by observing the feature vector, that means given a feature vector, you need to estimate what is the probability of a class, probability of class either C1 or C2. It means that by viewing the feature vector, what is the probability of this feature vector from this class C1 or from this class C2. So, this is known to be posterior probability. Prior probability means without any observation, estimating the probability or knowing the probability is known to be a prior probability. It means that we do not know about any observation vectors and all. So, from that if you just guess the probability, that is known to be the prior probability. Whereas, the posterior probability means by observing the feature vector, estimating the probability of a class of a particular observation vector, feature vector. It is known to be posterior probability. So, probability of Ck given XL can be computed like this from by using these two expressions. Probability of Ck given XL is nothing but whatever is here divided by probability of XL, right, because these two are equal, which are nothing but the joint probability. So, probability of Ck given XL equals to probability of XL given Ck times probability of Ck divided by probability of XL. And here as I mentioned, probability of Ck given XL is nothing but a posterior probability. It is nothing but the probability of a class by knowing the feature vector. Given a feature vector, estimation of the probability of this feature vector from this class, from the specific class, this is known to be posterior probability, right. So, this is a posterior probability, and the other one probability of XL given Ck, XL given Ck, it is nothing but just estimation of the probability of a feature vector conditioned to a class. This is known to be class conditional probability, class conditional probability. It means that we are estimating the probability of a feature vector conditioned to a particular class. For this class, what is the probability? It is known to be class conditional probability and all, class conditional probability, right, or this is also known to be probability density of X for a given class, and the probability of Ck is nothing but a prior probability, and the probability of XL is nothing but a probability of a particular feature vector, probability of feature vector without any condition, it is known to be unconditional probability, right. And this is you can see that for suppose there are n classes are there, C1, C2, C3, Cn. For all the posterior probabilities, you can see that the denominator is common, the denominator remains same. So, therefore, this denominator is known to be normalization factor and all, because this acts like a normalization factor, because if you sum up all of them, because probability of Ck given XL where all these classes C case, if you sum up, it should be 1. This should be 1. So, therefore, here you can say that this is the denominator is not to be normalization factor or not to be unconditional probability and here in case of a classification problem, what we need to do is that we will try to estimate these posterior probabilities for every class. So, in case of a 2 class problem, we need to estimate probability of C1 given XL and a probability of C2 given XL. We need to estimate the posterior probabilities, and from the posterior probabilities we have to decide the XL belongs to which class, either class 1 or class 2. So, how do we do that? By after estimating the posterior probabilities, we will try to see that whichever the posterior probability is the maximum, highest among all the set of posterior probabilities, then that the highest posterior probability can be hypothesized as the class label, right, because here in this case only you have 2 classes. So, therefore, we need to estimate the posterior probability of XL for C1 and C2, that means probability of C1 given XL and probability of C2 given XL, both of them have to be computed. Out of these two, whichever is higher, so that can be hypothesized as the class label of a given example or a given image and all, because we do not know, because with some 100 examples we will build the data and afterwards we need to check whether it belongs to class A or class B. So, for that we need to estimate the posterior probabilities, and then out of the suppose there are n classes, we have n posterior probabilities will be there, that means given a feature vector and that feature vector, with respect to that feature vector we need to compute the posterior probabilities of all the classes. So, whichever class having the highest posterior probability among all, so that will be hypothesized as the class label of a given thing. And here you can see, so here this particular plot is nothing but the posterior probabilities of the 2 classes, posterior probabilities of the 2 classes, right, because we have seen earlier in the when you are computing histograms at the very initial slides, you can see that even here also, if you look at the previous one here, you can see. So, these are nothing but histograms. If you plot the bin wise the number of examples, then it becomes a histogram of a class 1 and class 2, and you can see there is a overlap during these 3 bins. There are some examples belongs to class 1 and there are some examples belongs to class 2 also. So, therefore, corresponds to these, if you try to estimate the posterior probabilities, there will be overlapping you can be observed, because the probability densities of C1 and C2 there will be overlapping. So, therefore, during the overlap area, deciding that which class the example belongs to will be difficult, that prone to be error and all, that leads to error, because there are some examples which belongs to both the classes. So, therefore, here when you are trying to estimate the posterior probabilities, you can see here up to some point, so till from the beginning to here till this point, right, there is no class 2 examples at all. So, therefore, the posterior probabilities corresponds to class 1 given x1 up to this point will be high, is 1, that means there is no error at all. That means when you compute the x1 vector, if x1 falls here at the beginning, from beginning to here till this point, there is no error at all. We can safely say that the given feature vector or given image corresponds to the alphabet A without any error at all. And again from this point onwards, again if you try to, if the x1 happens to be here falls in this range from this point to the here, right, then you can safely say that the given feature vector corresponds to the image B, or image corresponds to the character B without any difficulty at all, without any error at all, almost like 100% accurate. If you can here, if the x1, if the vector x, if the estimated feature vector falls this side or falls from here to here, then there is no problem at all. We have the 100% accuracy with respect to the predicted class labels, but there is a misclassification that happens here between from this point to this point. Here at this point here there are few examples of B also falls here, and there are majority examples of A falls here, right, and as you go on the number of examples of B increases and number of examples of A will decrease. So, till this point here you can say the number of examples of A will be over, and here all the examples corresponds to B will be there, but during this region both A and B the features will overlap. So, therefore, So, this is the region where the misclassification can takes place. Sometimes you are lucky enough, your decision may be correct, sometimes your decision may not be, may be wrong also. But here during these regions there is no error at all. Here also there is no error at all, but this region where you have error and all. So, to have the, to minimize the error, if you take a threshold of this cross section of these two curves, whatever the threshold is there, if you take this threshold, we will get a minimum error and a minimum probability of error, right. So, here we will continue this lecture in the next class. So, we will stop here. Thank you.